All right, so I'm going to get started. For those of you who missed lecture on Monday, the announcements that you really need to know are the course website, which is at orgchemboulder.com. That has a copy of the syllabus, which I handed out on Monday, and also it's got a link to the lecture capture as of this morning. And it also has the typed chapter notes that I'm going to be lecturing off of. Also, as of this morning, Canvas, I think I've got the link to Sapling set up correctly. So if you go in and look at the assignments in this course, it should say use this link to set up Sapling or something like that. So use that link to set up Sapling. And after that, you should be able to just log into Sapling directly. Just you have to log in through that special link the first time in order to link the accounts so that when I try to sync up your grades, it will actually sync correctly. If you're having a hard time, let me know or contact the support at Sapling Learning people and they might be able to help you too. Okay, any questions about any of that? Okay, those of you coming in late, there are a few seats in the middle of the sections here, so you might be able to squeeze past people and find them. There's like a couple in this section, a couple right in the middle there, a couple on this side, one on this side. Yeah. Okay. Alrighty, so I just barely got into a little bit of chapter 1 at the end of lecture on Monday. So I'm going to pick up where I left off. So we were doing sort of a quick review of the Gen Chem material that's going to be most helpful for OChem moving forward. So the part of the periodic table we're really going to be focusing on are these top 3 rows and then a little bit of the halogens down here, which I didn't bother to draw in just yet. Okay, so last time we got up through pointing out that all of these elements are numbered in order, 1, 2, 3, 4, etc. And that is the atomic number, which refers to the number of protons in that element. Okay, so quick review on atomic structure, very quick review actually. Atoms have sort of a core or a nucleus, which I think just is Latin for like kernel. The nucleus, which consists of protons, which are positive, and neutrons, which are, like the name implies, neutral. So almost all of the mass of the atom is tied up in the nucleus. And then you also have, I'm going to draw like a really oversimplified, kind of inaccurate way of showing this for the time being. We'll get into a lot more detail later. But you also have these electrons that are located outside the nucleus in orbitals. Which are negative charged and much lighter mass-wise than the rest of the atom. So protons, number of protons determines what the atomic number is, which determines what element it is. So something with just 1 proton in the nucleus is going to be hydrogen. Something with 2 protons is going to be helium, and so on. The number of neutrons can vary and still be the same element. Usually it's somewhere between about the same number of protons and about twice-ish the number of protons, but it's a lot more complicated, and then there are some numbers that are good for stability and some that aren't. It's not super important, but if you change the number of neutrons but keep the number of protons the same, all that's doing is changing, I guess, what flavor of that element. Do you guys remember from Gen Chem what those different neutron having versions of the element are called? Isotopes, yep. So really the important thing to set which element it is the protons. That's kind of invariable if you're sticking with the same element. The only time the number of protons changes is if you're looking at radioactive decay, which we are not going to be doing in this class. So pretty much all of the chemistry that we're going to be doing is focusing on the behavior of electrons. Okay. So if we want to have a neutral atom overall, we have to have the positive and the negative charges cancel out. So the number of protons has to equal the number of electrons. So for example, if you have a neutral atom of beryllium, Be, which is atomic number 4, it's going to have 4 electrons in it if it's neutral. Okay, plus some number of neutrons, which is less important. Okay, so I said that this drawing of electrons is super oversimplified and inaccurate. So if we're really interested in the chemical behavior, we're going to have to dig a lot more into the structure and behavior of the electrons. So electrons fill into shells, otherwise known as orbitals, around the nucleus. And we're going to spend a little while towards the end of this chapter looking at atomic number, or looking at orbital descriptor numbers. But for the time being, we're just going to look at sort of the simplest way of calculating this. So we're going to just leave it as the smallest first filled in shell contains up to 2 electrons. And because I don't want to write out the entire word electrons every time, I'm going to use this abbreviation instead of electrons. I'm going to say E with a negative charge right next to it. Hopefully that's familiar from Gen Chem, but if not, that's what that means. And then all following shells, as far as we organic chemists are concerned for the time being, are going to hold up to 8 each. More once we get out to the larger shells, but we'll look at sort of what's going on there in a little bit. Eight is good for now, though. Okay, so the way this works is we're filling electrons into the shells. We've put 2 electrons into the first shell, which is closest into the nucleus, and then we can fill up to 8 in the next one out, then 8 in the next one out. So when we're filling electrons into these shells, we're going to end up with some shells that are filled and some that are maybe partially filled. So the filled inner shells hold what's called core electrons, and the partially filled shell at the outside if there is one, you might just have some filled shells and some completely empty shells. But if you have a partially filled shell, it's going to be holding what's called valence electrons. Okay, so based on this model, I guess it's not too surprising that pretty much all of the chemical behavior is not just due to the behavior of electrons, it's specifically due to the behavior of valence electrons, which kind of makes sense. The core ones are in inner shells. They're not as sort of out there on the edges of the atom as the valence electrons are. These are like where the atom actually interacts with the outside world. Okay. So the core electrons, since they are all filled shells, are actually going to have the same electron configuration as the next noble gas down the periodic table. So I'll show what that means in a second here. Okay, so for example, if we're looking at fluorine up here, actually let me use sodium as an example first because that's what I have in my notes. So, sorry, just for those of you watching this recording at home, I actually have the camera set so it looks at either the left side or the right side of the board. So if you see me in lecture switch from one side of the board to the other and not mess around with this control panel, let me know because that just means I forgot. Okay, so for example, sodium, Na, has how many electrons based on its position on the periodic table? So let me pull this down. Okay, so let me just fill in numbers 5, 6, 7, 8, 9, 10 for neon, 11 for sodium. So that means sodium is going to have the same core electron configuration as the next noble gas down, neon. So sodium, 11. As neon, which has 10 electrons. So those core shells consist of one innermost filled shell, 2 electrons in the first innermost shell, and then 8 in the next one. So that's its core configuration. And then sodium, the 11th extra electron, is the one valence electron that's in the third shell. Okay, so questions about that example? Hopefully that's familiar enough from Gen Chem, but if it's been a while, definitely like maybe work through a few more example problems like this. Okay. Okay, so similarly, any of the stuff in this row is going to have the same core electron configuration as the next noble gas down, which is neon. So like chlorine has the same core electron configuration as neon. It just has a bunch more valence electrons than sodium does. Okay. So usually when an atom wants to pick up a charge by gaining or losing electrons, so when an atom turns into an ion, in other words, it's usually going to do that by going to the nearest noble gas configuration. So for example, sodium, its closest noble gas is neon, numbers-wise. So sodium has 11 electrons. It's going to lose 1 electron to get exactly the same configuration as neon, 10 electrons. So sodium is losing an electron to get to the nearest noble gas configuration, which means that its charge is going to be what? Yep, positive. So this is kind of a common place where people get thrown off at the start of OChem. So sodium goes to sodium plus. Actually, I'm not going to circle my charges just yet. I'll do that later. So it's losing an electron, which means it's getting a positive charge. It's kind of tempting to say it's losing an electron. It must be down 1, so therefore minus. But remember that electrons are negatively charged, and so losing an electron gives you a positive charge. Okay. Similarly, chlorine, which has 12, 13, 14, 15, 16, 17, 18. So chlorine has 17 electrons, is actually closest in configuration to argon, 18. So if it wants to get there, chlorine actually has to pick up an extra electron. So it's going to go to argon configuration, 18 electrons. So chlorine's actually going to take on an extra electron, which gives it a negative charge. Okay. So any questions about those two examples? Okay, so something a little further from either side of the periodic table would have to lose or gain more electrons to get to a noble gas. So like sulfur would have to pick up 2 if it wants to be an ion. Magnesium would have to lose 2 and take on a +2 charge. So pretty much following the same pattern here. Okay, so what we're going to look at now is spending some time on different types of chemical bonds. One of these involves looking at the actual ions that we just learned how to make, and then one of them is a little bit more complicated than that. Okay. So the two biggest types that we're going to see, there are a few other sort of weird in-between subtypes, but the two major ones are ionic bonds and covalent bonds, which I'll cover in a second here. Okay, so ionic bonds are pretty much just straight up attraction between opposite charges. So if you've taken like physics class that covers sort of electricity and magnetism, it's pretty much just straight up positive and negative charges setting up a field that attracts each other. Okay, so probably the most commonly used example and the simplest one is table salt. So we already know that if it's made up of ions, we know that sodium ions are going to be Na+, and chlorine ions are going to be Cl-. You may remember that this is actually, once chlorine takes a negative charge, it becomes chloride. I'm not super going to be a stickler on naming the... Okay. So if we want to look at the structure of table salt, let's just use a couple of circles. So the empty circle here, I'm going to make chlorine. And the filled circle, I'm going to make sodium. So this just sort of fills into some sort of organized crystal structure like this of alternating ions. It's a lot easier to draw in 2 dimensions on the board. In reality, there's multiple different options for the most efficient packing method, and a lot of it kind of depends on what the ions are, how big they are, if they've got different charges, like how many nearest neighbors they each need. But it's some sort of ordered regular packing structure like this. So notice that there's no real directionality to this. Like there's no particular reason that this chloride ion in the middle here should be any more attracted to, say, this sodium one above it than it is to this one over here to the left. So each chloride is equally attracted to all its sodium plus neighbors. Okay, so if we put this sample of sodium chloride, this grain of table salt, into something that dissolved it, for example, water, all of these ions are going to completely split off from each other and go their separate ways. I guess I should put an asterisk next to that statement, because later on in Chapter 8, when we start looking at solvents, that's not 100% true, but it's good enough for now. Okay. To individual ions. Okay, so the ionic bond is really not a permanent thing. It's just sort of the charges pulling the ions together. Question?
Does solution imply water or?
So good question. So anything that will dissolve the sample, water is kind of a really good one for dissolving ionic samples because it has a high polarity, but we'll later on see other examples of high polarity solvents that would also work to dissolve this. But yeah, it's got to be something that has a strong enough concentration of positive and negative charges on the solvent to actually make it energetically worthwhile for these guys to split up. So, okay. Other questions about this one? Yeah.
This isn't necessarily a question about this, but for like the charges that are in the middle of the periodic table, which noble gas would
So the ones that are towards the middle of the periodic table, so like carbon and nitrogen and boron, for example, it's very rare that they'd actually form ionic bonds at all, just because by the time you have to pick up or lose like an extra 3 or 4 electrons, that's so high energy that it's pretty unlikely to happen like anywhere except in the vacuum of space or like in extreme conditions. In theory, yeah, I guess you could make a nitrogen with a -3 charge, but yeah, pretty much it's always just going to be like the first couple of rows before and after the noble gases that we really have to worry about. Okay, other questions about that one? Okay, so this is probably less relevant to organic chemistry than the other type of bonding, which we're going to be spending much more time on, which is covalent bonding. Okay, so these are a little bit more egalitarian than ionic bonds. Ionic pretty much involves an atom completely losing or completely gaining 1 or more electrons. Covalent bonds are sharing. So we're sharing electrons between atoms so that both of them can get a full shell going on between them, full noble gas configuration, without anyone having to give up or lose, anyone having to give up electrons entirely. Okay. So another name that tends to get used here instead of filled shell, because we're almost always looking at a set of 8 electrons, because most of the time we're looking at the second shell and upwards, this is where the term octet comes in. So octet means a group of 8. So the octet rule tells you that if we want a filled shell on something, it's usually going to have 8 electrons as part of its valence shell. The one case where that doesn't apply is when we're looking at things that only are using the first shell, where all it needs is 2 electrons. Which I guess would be a duet shell. Okay. So what we're going for when we're sharing electrons is trying to get a full octet or duet on both of those atoms. Okay, so the simplest example we could possibly use here is the 2 simplest atoms that we have on the periodic table. So hydrogen gas. Which turns out to have the formula of H2. All right. So the way that we're going to show this is with a Lewis structure. Also known as a Lewis dot diagram, where each valence electron is a dot. And then the shared electrons are dots that fill in between those 2 atoms. Okay. So shared electron dots go between 2 atoms, and you can show that either as 2 dots or a line linking them. Okay, so what we're doing here, we're putting together 2 atoms of hydrogen. Each one comes in with a single electron of its own, assuming that it starts neutral. We know that because hydrogen's atomic number is 1. That means it's got one proton, which means it's got 1 electron. So this hydrogen atom, we're going to draw as whatever its abbreviation on the periodic table is here, shows up with 1 electron. This hydrogen also shows up with 1 electron. And rather than going around with an unfilled valence shell, which we know is not as good as having filled valence shells, things like to have noble gas configurations, whether they have to share or not, what we're going to do is combine these together so that both atoms get to use both electrons towards their shell configuration. So now this one has what counts as 2 electrons in its outermost shell, so it's got the noble gas configuration of helium, 2. And same for this one. It's also got a full duet. It's also happy. Okay, so we can draw it as 2 dots linking them, or we can combine those dots into a single bond, a single line linking those 2 atoms of hydrogen. Okay, so questions about this one? Yeah.
So you were talking about how like the ones in the middle of the table are going to require more energy to form ionic bonds.
Mm-hmm.
Does that mean ionic bonds in general require higher energy to form than covalent?
That depends. I guess, so ionic bonds, I guess in general, like the more concentrated charge you have in one location, the higher energy that's going to be. And so like if you're trying to make something with like a -4 charge on it, that's going to be pretty inaccessible compared to like this nice easy chlorine with a -1 charge. Between the two, really it kind of depends on what all is going on in the environment. Usually things that are pretty close to having a noble gas configuration are going to make ionic bonds more easily, but they can still do covalent bonds depending on what else they're looking at bonding to. Yeah. Okay, good question. Any other questions about this example before we move on? Okay, cool. So let's do a little bit more complicated one. So let's look at methane, which is CH4. Okay, so this has 1 carbon atom and 4 hydrogen atoms. I'm going to just erase that part of the board over there. You guys get to see my sweet lecture bucket squeegee thing. I guess side note, when I lectured in this room in past years, if you only use the dusters to erase the board, it gets super smudgy and hard to read, and it's pretty much impossible to read on the lecture capture. So I'm kind of in the habit of just washing the boards down in between use. Okie doke. So let's look at methane as another example. So we know that carbon has atomic number 6, so it's got 6 total electrons. How many of those are valence electrons? 4, right? So carbon has 6 electrons, of which 2 electrons core, because that's filling in the first shell's 2 electrons, which means the leftovers, the remaining 4 electrons, are valence. So we only show 4 dots around carbon, not all 6. And hydrogen, we already know, just has the 1 electron total. So that's easy. Okay, so what we're going to do is show carbon here with 4 dots. Usually we're going to space those out so that we can make room for the bonds that it's going to make. We're also going to use 4 of our H dot, H with 1 electron on it. Okay, so what we're going to do is, we know that to make a bond between carbon and hydrogen, we have to stick 2 electrons together. So I'm just going to take each one of these H dots and plug it into one of the 4 sides on carbon. So it might help to space them out a little bit like this. So I'm going to take carbon here, I'm going to plug in an H with its dot on one side, H with its dot on the other side, H with its dot down here, and H with its dot over here. So there's room for 4 total hydrogens. So notice that this is a great stable structure because hydrogen, each of them has the 2 electrons in its shell that it wants. Or a full duet on hydrogen. And then the C has 8 electrons around it, which is also a full octet. Okay, so atoms are always trying to get to a full duet or octet. That's where they're most stable energetically. We'll cover some examples where that turns out not to be the case in a little bit here, but that's kind of generally what you're aiming for when you're putting together these structures, is get a full octet on everything, unless it's hydrogen, in which case get a full duet. Okay, and then another way that I could have drawn this is just lines linking each of the atoms. So carbon with 4 bonds coming off of it to 4 of the H's. Okay, questions on that example? All right, cool. So let's do another one which has something that we haven't seen specifically yet, and that is water. Which hopefully you're aware is H2O. Okay, so hydrogen, like always, shows up with 1 electron. Oxygen has 8 total electrons because it's atomic number 8, but 2 of those are in the first core shell, so it has 6 electrons that are valence. So we're going to have oxygen here. We're going to start going around it and filling in the electrons. So we're going to put 1 on each of the 4 sides, kind of like we did for carbon, but we still have 2 more to spend. So let's sort of make a second path around the atom and fill in 2 of those remaining electrons as we go around. And then we still have 2 of our H dots to build with here. Okay, so I'm going to do pretty much the same thing that I did with CH4. I'm just going to draw oxygen with the electrons on it. And then I'm going to show up with 1 H dot, plug it in on this side. The other H dot I can plug in over here. Okay, so again, quick check. Each hydrogen has a full duet. Oxygen has a full octet. Everybody's happy. Okay, so I can draw that also as oxygen with 2 bonds going out to hydrogens, but I can't combine the 2 electrons on the oxygen here into a bond to anywhere because they're just on the oxygen itself. So I'm going to leave those as they are. Okay, so these electrons that are just on the central atom, not shared, these are called lone pairs because it's a pair of electrons that's not actually being shared with any atoms other than the one that it's attached to. So those belong solely to the oxygen, and they're not used for any sort of bonds. Okay, so these are actually vitally important for being able to do chemistry a lot of the time. We're going to talk a lot more about those in addition to looking at covalent bonds more. Okay, so questions about that example? Okay, cool. All right, so we are also going to see examples of cases where more than one pair of electrons is shared between 2 atoms. So you can share multiple pairs of electrons. So example for this one is ethene, known under the old school naming as ethylene. You may be familiar with this. It's the gas that sort of causes fruit to ripen. So if you throw a banana in a paper bag with some peaches, the peaches will get ripe a lot faster. It's because the bananas release a lot of ethene or ethylene. Okay, so ethene is C2H4. So let's see if we can build that one. we've got 2 of our carbon with 4 valence electrons. And we've got 4 of our hydrogen with 1 valence electron. Okay, so if we start doing the same thing that we did with building methane up here, and we start so there's carbon with 4 electrons. Maybe let's try building a single bond onto the other carbon. So we get that, and now we can start plugging in hydrogens. So we're going to go hydrogen up here, second hydrogen, third hydrogen, fourth hydrogen. But now we run into a problem. Hydrogens are all happy. They all have their full duet, but the carbons each are under an octet. Both of them only have access to 7 electrons right now. So the way to fix that is we're going to have to share more than 1 electron pair. So I'm going to erase these 2 dots on the outside and throw them into the middle as a second shared pair. So now this carbon gets to count 1, 2, 3, 4, 5, 6, 7, 8 electrons in its octet. And this carbon also gets to count 1, 2, 3, 4, 5, 6, 7, 8 electrons. So that's how they both sort of combine forces to get a full octet for both of them. So again, each pair of electrons you can show as a line. So if we want to do that for this 2 electron pair kind of thing, we're going to show it like this. So those carbons have what's called a double bond between them. As opposed to the single bonds, which have been linking every atom that we've shown so far in these examples. So the single bond is 1 pair of electrons. Okay, questions about that example? Okay, cool. So we can push this even further and show up to 3 pairs of electrons being shared. So if we're looking at ethine, which under the old naming would be called acetylene, which you may be familiar with because it's used for welding, is C2H2. So this one's going to look like 2 of our carbon with its 4 valence dots and 2 of our hydrogens with their single dots. So when we start putting this one together, again, we can start out maybe experimenting with a single bond between the carbons. But then when we go to plug the hydrogens in, we're going to come up pretty short of an octet on both those carbons. Each of them only has access to 6 electrons right now. So if we want to fix that, we can first go to a double bond. Maybe let's bump these 2 electrons into the middle as a shared pair. We're still shy of an octet though, so let's erase these 2 guys and bump those into the middle as a shared pair as well. Okay, so we're sharing a full-on 6 electrons between those 2 carbon atoms. So we can also write this as carbon 3 lines to the next carbon, so a triple bond, and then have the hydrogens coming off of each one. Okay. So for the stuff that we're going to look at in organic chemistry, it maxes out at a triple bond. You can't share 4 pairs of electrons for reasons that we'll see once we get into orbital geometry. Turns out once you are up in the higher ends of the periodic table, you can actually, but it's pretty rare that you can share more than 3 pairs of electrons. Okay, so another way to describe what we're playing with here, sorry, did I see a hand go up just now? Is someone stretching? Okay. So another way to describe how many pairs of electrons are shared between two atoms is with what's called bond order. So this is the number of bonds or shared electron pairs between atoms. So in other words, ethene here has a bond order of 2. Ethyne has a bond order of 3, or a triple bond. Okay, so we're going to see other descriptors of bond order later on, but that's when we're looking at the Lewis dot diagram, it's pretty much just as simple as how many pairs of shared electrons are there. Okay, so one last example before we break off for the day is Lewis structures where there's an overall charge on the whole deal. Okay, so this boron with 4 fluorines attached to it and a negative charge is the tetrafluoroborate anion. Don't need to know that. But the way we're going to put this thing together is boron's atomic number is 5, so it's got 3 valence electrons. Looks like this, 1, 2, 3. We also have 4 of the fluorides. So fluoride has 7 valence electrons. So it's got all but 1 of its core, of its octet filled in. But because we have a negative charge on the whole thing overall, we're just going to show that as an extra dot that we have to fill in somewhere. So that extra electron there we're going to have to plug in somewhere when we're done with this. So the way we can do that is boron here. We're going to start doing pretty much what we did up here with carbon and hydrogen and so forth. We're going to plug in fluorine on this side. We're going to plug in a fluorine on this side. We're going to plug in a fluorine down here. We can try plugging in a fluorine over here. Fluorine's only bringing 7 electrons with it. So if we stop there, we're just going to have like this weird half a bond, like only 1 shared electron between fluorine and boron. So that's where the extra electron comes in. We can plug that in there and finish building the bond between boron and this 4th fluorine. Okay, so the way that we show an overall charge on this deal is we draw square brackets around the whole thing, and we say this whole thing has a charge of negative -1. So there's an extra electron in here somewhere. We're being non-specific as to exactly which one it is, but it's charged overall. We can also draw this as this. Okay, so next lecture we're going to look at how to pin down exactly which atom is holding that extra electron.